Welcome to Prescribed by Dr. Nathan Goodyear, where integrative oncology meets holistic healing. This podcast is your home for the latest in innovation, exploration, and elevation in all areas of integrative oncology, medicine, health, wellness, and beyond. Join me and a host of other innovators as we go from practicing to prescribing. Your daily dose of wellness begins now. Dr. Nathan Goodyear, welcome to another hot take. I recently did a reel congratulating Chris Wark and his platform and what he's done to really provide hope, a beacon of hope for people with advanced cancer in an industry where little hope is there. Chris Wark has told his story repetitively where he's overcome advanced cancer by doing a lot of natural work. Now, he then touched on the need to recognize that we must move beyond ivermectin because the tide is going to be turning on ivermectin as a repurposed medication on oncology. And then we just need to simply move to artemisinin because it's natural, number one, but it's holistic and it's an antiparasitic too, and it works better. So I want to dive into the science when we focus on all things, particularly natural and holistic and integrative therapies, because simply focusing on those, we must still follow the science. We can't just say at the same that conventional medicine, de facto, we don't have to discuss the science because it's conventional. We can't say we must ignore the science because we're talking about natural, holistic, and integrative. On both, we must follow the science, not make it up as we go. So I put together a little presentation. At the end of this, you can access the study show notes, which will actually also have the references supporting everything that we're going to be talking about here. And of course, I must also mention that I have an online digital course on repurposed medications in oncology, module 1, many more to come, where we touch on the history of repurposed medications in oncology, ivermectin, mebendazole, fenbendazole, and mebendazole versus fenbendazole. But of course, what's happening there, it's being censored because of the word ivermectin, mebendazole, and fenbendazole. If you go to metabolicregen.com, you can find it there and purchase and take a deep dive, really deep dive on repurposed medications in oncology in module 1. So what we're looking at here is artemisinin versus ivermectin, a comparison of these anti-cancer medications. Now, I think the statement that was made in his reel was a faulty generalization. And this is critical because what he was saying was, well, they're both antiparasitics, artemisinin and ivermectin. And so because that, then we can extrapolate out beyond that. So they're both antiparasitics. Both groups won Nobel Prize of Medicines in the same year. So de facto, they're both effective. And de facto, one is better than the other because one, ivermectin, gets a lot of negative pushback. Well, a lot of that is no science. So what I want to do is focus on that here. And we must understand a crucial distinction here. Artemisinin and ivermectin. Their mechanisms, their cellular targets, the signaling pathways, their anti-cancer potential, they're distinct. They're different. Irregardless of the two teams winning the Nobel Prize in Medicine or the fact that they're both antiparasitics. We got to bridge the divide. And this is basically a problem that I'm seeing happening in medicine. There are a few trying to bridge it. What's happening is it's a zero-sum game. It's all natural or it's all conventional, and there's no in between. The problem is everything's in between. And when we look at this zero-sum game, it is also a faulty generalization. Natural therapy has its role. I love natural. No place I want to be than natural. Holistic strategy. Conventional therapy, it can have a role too. It has a need too. You walk outside and break a hip, no amount of vitamin D is going to help you there. You need surgery to repair that. Thank goodness we've been blessed to know how to do that. If you have a metastatic tumor in your brain and it's causing massive edema at risk of herniation in acute, emergent, life-threatening situation, guess what? We have the ability to stereotactically go in there and radiate that. But now couple that with natural holistic therapies to reduce the need for steroids and improve the healing. Guess what? That's integrative. It's working with the body to both target the tumor and heal the body simultaneously. And so we don't want to look at this as a zero-sum game, but we want to say these therapies work together. And the bridge there is integrative oncology. And in fact, it's really holistic medicine that is really the best strategy, because it's taking the best of everything to look at the perspective of the individual in a holistic perspective. That concept, holism, was first born out of a book in 1926 by a South African statesman by the name of Smuts. And he was very frustrated with the compartmentalization that existed in education and business. He said, if we compartmentalize all these things and never reconnect them, they're never reconnecting back to the whole, which is the whole intent. And that's exactly what a holistic strategy does. In medicine, everything's compartmentalized. Go to all your different specialists and you see that. And then the question I always get is, do these different specialists communicate? Not so much. So then what's lost is the impact on the whole. That's the individual. We have to recognize the individual, the whole, is the benefit. So even though we may break things down in compartments to understand them in the complexity that is disease in the body and natural and holistic and conventional, they must come back together for the benefit of the whole, the individual. So let's touch on this first, because this statement was correct. Both the group that was involved in artemisinin and those involved in ivermectin both won Nobel Prize of Medicine in the year 2015. The team for artemisinin was Yo-Yo 2. This was led by the Chinese government looking for a safer, better alternative for malarial treatment. And they were looking specifically at artemisinin. And when you look at the treatment of malaria right now, artesunate, which is a semi-synthetic derivative of artemisinin, is considered the gold standard treatment there. Now, artemisinin isolated from the plant Artemisia annua. To show you how much I believe in this therapy, I took 2 overnight trips to go visit a university in the country of Mauritius and connect with the people in Madagascar, where this therapeutic is instrumental in how their culture targets cancer. I believe in this therapy, been using it a long time. Of course, now the derivative here, artesunate, is a gold standard for malaria, and one of the most readily available is Plasmodium falciparum. And this, in turn, has saved millions of lives. What a discovery. The impact is tremendous and really, in a way, second to none. Now, when we look at ivermectin, same year, Nobel Prize of Medicine and Physiology. And 2 people, they shared it here, Satoshi Amura and then William C. Campbell. Now, what they discovered was avermectins. And from the avermectins, they were able to develop ivermectin. Now, the avermectins were discovered in the soil from a single-cell organism from Streptomyces avermytis. And this is where we got avermectins, and this was found in the soil in Japan. Now, William C. Campbell, he helped to purify this and basically bring this to an effective anti-parasitic agent. And so what we have here is definitely a true statement where 2 antiparasitics targeting parasites, but we'll touch on differences here in a second, and also winning Nobel Prize of Medicine in 2015. But honestly, that's where a lot of the connections end. And we'll dive into which one's better, which one's not, what's the level of evidence. But when you look at the difference, I already mentioned that artemisinin actually was developed for malaria, but when you look at ivermectin, it's very effective and it's approved for onchocerciasis and also for lymphatic filariasis, even ectopic parasites such as scabies and lice. Now, the potential anti-cancer mechanisms between the two are very, very different. So here's just a summary of the shared history, but divergent paths. Again, both antiparasitics, both working to target cancer, but in different ways, both winning a Nobel Prize in Medicine in 2015. And so let's get into the different impacts here, okay? Now, I think we must recognize that artemisinin first has many different derivatives, okay? There's artemisinin, there's really the active form, which is dihydroartemisinin. So if you take artemisinin naturally, it gets broken down, metabolized into dihydroartemisinin. There's also a beta artemether form, and then artesunate, which we'll touch on in just a second, is actually the best delivery form, which is the semi-synthetic derivative. But now understand even artesunate gets converted back to the dihydroartemisinin form. So we'll touch on that in just a second. Again, all coming from the plant Artemisia annua. This is sweet wormwood. So artemisinin is the natural, dihydroartemisinin is the most active, and artesunate is the semi-synthetic derivative but most effective. Ivermectin, again, a macrocyclic lactone derived from Streptomyces avermitis. It is FDA approved for an antiparasitic here, a variety of different ones that I just mentioned, the river blindness and the strongyloides and the ectopic parasites. And then, of course, for artesunate, it is approved for malaria. So both of these are approved via FDA, but the artemisinin is that natural form. And there's no natural form, quote unquote, of ivermectin. And saying that artemisinin is the natural form of ivermectin is wholly scientifically inaccurate. So again, artemisinin versus artesunate, because we have to carve those out just a little bit, both from the same source. The problem with artemisinin is that it's very naturally lipophilic, has poor water solubility, and so it has very poor oral absorption. And again, it's metabolized into the active form dihydroartemisinin. When we look at the semi-synthetic derivative, that's artesunate, that is the one that all the research has been done on. So when you're talking about artemisinin as an anti-cancer therapy, and we'll talk about that in just a second, the research is artesunate, where it's really been shown to be effective. Now, I think there is some research showing that artemisinin can have some benefit. The problem is it must be converted to our dihydroartemisinin, and the oral route of delivery is a big problem. The great news about artesunate is it has better water solubility, and it does again get converted back to dihydroartemisinin, but it's great in IV, it's great in IM, it's great in oral, it's great in rectal, but there's different pharmacokinetic properties there that provide preferential use of artesunate. This is why it's been used, it's stable, it's highly effective, and that's why it's been FDA approved. Artemisinin is natural, but it is the source for artesunate, the best delivery technique, though it both still end up producing dihydroartemisinin. And when we look at the artemisinin core anti-cancer mechanisms, we have to understand these are going to be different than ivermectin. They're going to be shared with artesunate. Clearly, just artesunate's a better form. So it's an iron-dependent activation. See, when cancer is growing rapidly, it pools iron. It's actually called a labile iron pool. It actually triggers the gut to reabsorb iron very quickly. It transports it with ferritin. It transports it with transferrin receptors so that it gets uptaken into the cancer and the cancer environment to pool it. It actually blocks the ferroportin. These are portals that transport iron out, so that then the medium of the cancer becomes very, very rich in iron. And here steps in the benefits of artemisinin or artesunate. They actually have endoperoxide bridges that can interact with ferrous iron, that's Fe2+, create a fit-and-like reaction in this highly rich iron environment to actually trigger a type of programmed cell death dependent on iron called ferroptosis. My good friend Jane McClellan has written extensively about this. If you haven't read her book, I encourage you to do so. She has a great resource, and she's a dear friend. Mitochondrial dysfunction, also artemisinin, is also affecting membrane depolarization, thus leading to intrinsic apoptosis, another form of programmed cell death, but doing this down through cascade activation of capsaicin. Again, apoptosis, another form of programmed cell death, not dependent on iron, like we just mentioned with ferroptosis. What's also good about artemisinin, it actually inhibits angiogenesis. Great, great tool. This is the blood vessel growth that cancer so desperately needs to survive and thrive on. Artemisinin downregulates vascular endothelial growth factor that is triggered by hypoxia-inducible factor 1 alpha. Hypoxia regions within the tumor are one of the major drivers of many of the cascade effects, signaling pathways that promote cancer's survival and thriving. And here, artemisinin directly targets that, impairing its growth and metastatic potential. It modulates the immune system. Now, this is important because it's reprogramming macrophages that are recruited to the tumor microenvironment. These are called tumor-associated macrophages. Just because we recruit immune cells to the environment doesn't equate to good or bad. Just because we stimulate the immune system doesn't equate to good or bad. Just because we stimulate inflammation, that doesn't equate to good or bad. Because when you recruit immune cells, such as macrophages here, these Hypoxic and iron-rich areas, guess what? They cause macrophage polarization where you get a shift of M1 type macrophages to M2 type macrophages, which M2 type macrophages are pro-tumor. They support the tumor, but they're immune cells, but they've been recruited there. But the environment created by that cancer actually manipulates them to favor it. See, cancer will draw the immune system to itself, and then it'll turn the immune system on the immune system to support itself. So artemisinin actually reprograms these M2 macrophages back to M1 macrophage. So here's just a quick comparative pharmacokinetics looking at this. The process of, what we're looking at with artemisinin is it just has such limited oral bioavailability. Most of the research is not done there. Obviously, when we're looking at artesunate, research highly supports this technique, though it's not the natural form, it's a derivative of the natural form, artemisinin, but it's the best studied and it's highly effective when given IV, oral, IM, sub-Q, rectally, however you want to get it. And it has rapid peak IV dosing. When you combine it with vitamin C, powerful tool there. So artemisinin, not FDA approved, natural therapy. It's a good therapy. Okay, the problem is it has poor oral bioavailability, just not absorbable, not effective. Now I know you can give it IV, but I think still we're not dealing with the benefits related to the artesunate because the exact dosing is not known. The artesunate, we have a good understanding of the dosing there. We have a good understanding about the toxicokinetics of artesunate versus artemisinin, and in actually human studies and using this in sick individuals such as in malaria, but also in cancer. So FDA approved 2020 for IV treatment of severe malaria for adults and children in the US. But of course, how many people do you know have been diagnosed with malaria? So you just don't see it really used much. And oral artesunate is used globally for the malaria treatment as well. So the shared anti-cancer mechanisms of both artemisinin and artesunate, again, the intermediate, which is the dihydroartemisinin, is really the active component. The iron-dependent activation, the ferroptosis induction, the mitochondrial membrane depolarization triggering apoptosis, the anti-angiogenic effect, and the immune modulation. It just comes down to which is the better delivery route. I love natural, I love holistic, but we must be effective. We must be effective. And so what we can do is take the natural perspective and we can then use that to the benefit of the fight against cancer, but also the benefit of healing the body simultaneously. Another integrative strategy. Now, when we look at the difference, because I've referred to this many times, between artemisinin and artesunate, artemisinin, most of the research on this is in vitro. So this is pre-animal and pre-human. I'm not aware of any human research on artemisinin. There's less favorable pharmacokinetic studies on it showing that it just doesn't have the efficacy that you need to liberate, absorb, distribute, metabolize, and excrete in that process of pharmacokinetics to be highly effective, not just against cancer cells, but against tumors at large. Now, there are in vivo studies on this, but it's looking at a lot of the derivatives, and it's not really looking at the efficacy of artemisinin. And again, when we look at artesunate, definitely most of it is preclinical, but here we actually have some human clinical trials showing its superior bioavailability, its high rapid systemic delivery, and its improved tolerability and its ability to be stable for actual use. And when you look at all the human cancer trials, for those including colorectal cancer, those looking at small cell lung cancer, and cervical intraepithelial neoplasia type 2-3, as you see here, in the artemisinin arena, it is with artesunate. So we can't extrapolate that because artesunate is from artemisinin, if we give artemisinin, it's going to do the same thing as artesunate. Though that may seem to make sense, that's not evidence-based. So what we want to do is use natural therapies to be effective. So the implications in oncology, the kind of translational effect, is that these are highly effective, but it's all going to be artesunate if we want to be effective per the science. The best delivery route, I believe, per the science is IV, especially when you're dealing with a high metastatic burden disease. And again, we must follow the science here. Now, ivermectin, another antiparasitic, ivermectin, an antiparasitic that also won the Nobel Prize in Medicine Physiology the same year, 2015, as artemisinin, also another antiparasitic. Its anti-cancer mechanisms are different. So you can see what we're doing is showing that, yes, they're antiparasitics. Yes, they both won the Nobel Prize in Medicine in 2015, but that's where the similarities in. Beyond that, they're quite different. And thus, they could maybe actually be used effectively in synergy, stack them together to be effective. So when we look at ivermectin, its core anti-cancer mechanisms, the Wnt or WNT beta-catenin pathway inhibition is one of its major pathways, actually impairing migration, invasion, and metastasis potential. Now, it does affect mitochondria, but here it's actually inhibiting the complex 1 in the mitochondria, that's creating energetic stress and an energy crisis, actually elevating reactive oxygenation species, increasing oxidative stress, and this thus leads to the triggering of apoptosis of the cell. It actually blocks important alpha beta 1 dependent nuclear transport, which is transporting oncogenic signals across into the nucleus to accelerate and fuel cancer's metamorphosis and growth and thriving. It also inhibits epithelial to mesenchymal transition. Now, it suppresses it. Epithelial mesenchymal transition is two cell types, epithelial and mesenchymal. Epithelial is stable, mesenchymal is more mobile. So there's different characteristics between these two in describing it. What we're describing here is the ability of cells to move from a stationary, immobile, to a mobile, modal environment type. And that's what epithelial to mesenchymal transition does. Cancer does that very effectively. Now, what we're looking at as it relates to our ivermectin, it actually inhibits that mobility from immobile to mobile, keeps it immobile. Now, what about the hallmarks of cancer? Because Hanahan and Weinberg in 2000, 2011, 2022 published and then added on to in 2011 and 2022 what are called the hallmarks of cancer, really diving into the mechanisms. Because again, if we're going to talk about the use of natural therapies, which I love to, if we're going to talk about the use of repurposed medications in oncology, I love to. We don't just throw those on the wall and hope they stick. We must understand these must be used with intended purpose, precise, the right treatment and for the right patient, the right combination, the right time for the right person. And when we are looking at these hallmarks of cancer, it's showing just that. These have a very precise intended benefit and target. So when we look at ivermectin targeting these hallmarks of cancer, again, check out the show notes, you'll find those there. We see that it targets the hallmark of cancer resisting death by triggering apoptosis and autophagy. It targets the hallmark of cancer sustaining proliferative signaling by inhibiting proliferation, evading growth suppressors by actually overcoming the drug resistance and storing sensitivity of the tumor cells to actually treatment, chemotherapy, or radiation. Evading immune destruction, key rate-limiting step in how cancer survives and thrives. Guess what? Here, ivermectin actually modulates the tumor microenvironment to turn cold tumors hot. These are non-immune responsive tumors to hot immune responsive tumors. People say, well, what about, I use natural killer cells, I'm using dendritic cells. Well, what if they can't get into the tumor microenvironment? What if the immune system keeps them out? You could give all the natural killer cells in the world systemically, but if the cancer blocks their ability, same way with dendritic cells, to infiltrate, to actually then work against the tumor, they won't work. That's called cold tumors, and the majority of tumors per research are cold. They keep the immune system out. Even if you give it systemically, they keep it out. That is a desert environment. It is an environment of the tumor microenvironment that is deserted of immune cells. The best strategy there is actually to change the signal, modulate the immune system within the tumor microenvironment so the immune cells are actually recruited there. And guess what? You happen to do that with the intratumoral ablation and intratumoral immunotherapy approach. But here, ivermectin also it inhibits angiogenesis, thus targeting the hallmark of cancer, the induction of angiogenesis. Now, artemisinin, the core anti-cancer mechanisms, looking through the hallmark of cancers, again, from Hanahan and Weinberg, they target the sustaining proliferative signaling, invading growth suppressors by inducing, they stop the cell cycle growth at the G2M phase, and they also interfere with the P1-3K, AKT, mTOR pathways. They trigger and interfere with STAT3 and nuclear factor kappa beta, major inflammatory transcription factor. They also target the hallmark of cancer resisting cell death. They also, and here, they're triggering apoptosis, autophagy, ferroptosis. They target inducing angiogenesis. So similarities between the two, but the mechanisms by which here they're inducing the blocking of angiogenesis is a little bit different. Activating invasion and metastasis, another hallmark of cancer. Here, artemisinin is actually targeting matrix metalloprotease type 9, incadherent and vimentin, actually interfering with epithelial to mesenchymal transition, also deregulating cellular energetics. Here we have artemisinin targeting hypoxia-inducible factor 1 alpha to actually restore cellular energetics, because deregulated cellular energetics is a key part of cancer, hallmark. Cancer immunity evasion and modulating the tumor microenvironment. This is the hallmark of cancer that artemisinin is targeting by working to basically modulate the tumor microenvironment again and make it more pro-tumor. It's going to be more anti-tumor rather than pro-tumor. And then it targets stem cells. Here, artemisinin targets stem cells just like ivermectin does, but again, via different mechanisms. So though they can actually target the same hallmarks of cancer, as described by Hanahan and Warburg, their mechanisms by which they do that are almost universally different. So here we have antiparasitics, both Nobel Prize winners, same year. But beyond that, very, very different, especially when we dive into the science as to what they actually do. Because the reason why they're anti-cancer is not because they're anti-parasitic. So you have to recognize that cancer and parasites have a lot in common, right? Parasites are introduced into the body. Yep, cancer can be introduced, such as with viruses and bacteria and even parasites. So cancer then grows. What parasites grow? Cancer then evades the immune system. Parasites evade the immune system. Parasites spread and cancer spread. So when you see the similarities, it doesn't de facto mean cancer is a parasite, okay? What it means is they have very shared signaling pathways. And when you look at these antiparasitics, the reason why they're showing anti-cancer potential different between these two antiparasitics, artemisinin and ivermectin, is because they're targeting different pathways. But universally, they can target some shared pathways, but they are different. So ivermectin and artemisinin, what about the overarching research? I think we have to look at ivermectin as broader preclinical reach, meaning in terms of the specific multi-omics, genomics, epigenomics, transcriptomics, metabolomics, immunomodulamics, exactly what are the pathway and the pathway signaling that ivermectin is disrupting. There's actually more research showing it's broader research, but the actual research translating into humans is very, very limited here. Almost all of this is cell and animal, so that's preclinical. Preclinical is when you get to human studies, but still a lot of exciting research here. Now, there's great opposition pushing against that advancement, so I believe there is intentional slowing of that movement. This drug is very safe. There are those that would say it's safer than Tylenol, and that's why they're pushing it over the counter. But what I would say about that is, well, if everybody was using Tylenol as indicated per the research that got it put over the counter, guess what? There wouldn't be an issue. The problem is people aren't using it as intended, as directed, and you put something like ivermectin over the counter. My concern is people are going to be using it not as intended, not as a directive, and actually using it with other therapeutics, of which are going to affect its safety profile. Now, artemisinin has much more emerging clinical signals, meaning it's got much more research showing, though still limited, on its impact actually in humans in an anti-cancer role. So it has a greater clinical signal, whereas I would say the ivermectin has a broader preclinical reach. So very, very different in their efficacy, and I think where their current research tells us they are. Now, there's been much more embrace of artesunate and artemisinin by the clinical research world, less by ivermectin. I think that's borne by, 2019, 2022. But there's no head-to-head studies, again, that I've been able to find to actually see that, one's better than the other. So saying again, artemisinin's better than ivermectin because the push is to censor ivermectin, which again, ivermectin's censoring my course right now, though there's plenty of research, 459 at the time of the publication of that study. But when you look at artemisinin and artesunate together, you're looking at over 2,000. So I think there's an intended push to keep ivermectin from advancing, whereas that has not hit artesunate and artemisinin at current. So I think there's an explanation of why there's more clinical signal with artemisinin and artesunate and less with ivermectin, but definitely there's more deeper, broader preclinical reach, I think, with ivermectin over the artemisinin and artesunate. Again, don't take my word for it. Go check out the studies, take your own deep dive. So that's been the hot take on artemisinin, artesunate versus ivermectin. Again, no zero-sum game. We're not going to take any fallacies here and run with it. We just follow the science. So again, shout out to those that are using natural therapies. I love them. I use them in conjunction with both integrative, other natural therapies, and conventional when we need it. We have to understand that our purpose here is to heal patients. Our purpose here is to eliminate cancer. That's not going to be done through a magic bullet. Cancer is not caused by one thing, the magic bullet, Paul Ehrlich, early 20th century. It's not going to be treated with one thing. The best strategy is to integrate therapies together, natural, holistic, integrative, herbal, nutrition, with conventional. And it's that umbrella that integrative oncology provides that truly will allow the compartmentalized segments of therapy and of cancer to work back together to work to treat the whole individual, to eliminate the tumor, to optimize the immune system, and heal the body. That's another hot take by Dr. Nathan Goodyear. Thank you for joining us on this hot take. I encourage you to please subscribe and share to others so that they can hear about this. And again, check out the info below, the show notes, to get access to this and other supporting information. I will see you on the next hot take by Dr. Nathan Goodyear. Thanks for joining us on this episode of the Prescribe Podcast. All references supporting this episode can be found on the prescribe.com website. That's pre-scribe.com. To get your next dose of medical innovation, make sure you subscribe to Prescribe. We'll see you for your next refill.